Tree diagrams and conditional probability. Let's say that Jasmine plays Priya at tennis, and the first to win 2 sets wins the match. We're going to illustrate this sample space using a tree diagram. So the tree diagram works like this. We have 2 people playing, so Jasmine and Priya, and let's say that these letters represent Jasmine wins the first set and Priya wins the first set. So then they play a second set. So either Jasmine can win the second set or Priya can win the second set. And if Priya wins the first set, then Jasmine can win the second set or Priya can win the second set. Now, because it's the first to win 2, if Jasmine wins both, then we'd stop. So we don't need to put another branch off of there. But if Jasmine wins the first and Priya wins the second, we need to play another set. So it could be Jasmine there and Priya there. Similarly, here, Priya, Jasmine, if they split the first 2 sets, then we're looking at going into a third set. But if Priya takes both sets, then we can stop. So this is an example of a tree diagram. They are useful when the events are sequential, but that doesn't mean that they're only used when events are sequential, and it doesn't mean that if the events are sequential that you can only use a tree diagram. It's just one way to illustrate your sample space, and these can be used for dependent or independent events. Carla is having bad luck. Her car will only start 80% of the time, and her motorbike will only start 60% of the time. We're going to use a tree diagram to determine the probability that both will start, only the car will start. We're going to find the sum of the probabilities and the probability of at least one vehicle starts. So similar to what we did with that tennis match, we're going to have, let's say that the car will start, and then let's put a C with an apostrophe to represent the car not starting. And then the probability of the car starting is 0.8. The probability of the car not starting then is going to be 0.2. Then we can branch off of there with a motorbike. So the motorbike can start or the motorbike cannot start. And same thing down here. It doesn't matter. These will be independent. The car starting and the motorbike starting will be independent of each other. And the probability of the motorbike starting is 0.6. So the motorbike not starting is 0.4. And we can just repeat that down here. So the probability that both will start would be these branches here. And we're going to simply multiply. You can think about this as the car will start and the motorbike will start. Remember, and would mean multiplication. So the probability that both start is 0.8 times 0.6, which is 0.48. I'm going to put that up here. Okay. Then for part B, the probability that only the car will start. So then we're looking at the car starting and the motorbike not starting. So probability only the car starts would be 0.8 times 0.4, which is 0.32. Now for part C, we want to find the sum of these probabilities. So what I'm going to do is I'm going to actually write down the individual probabilities for these 4 scenarios next to them here. I'm going to do this in a blue color. So this one was 0.48. We already did that. This one is 0.32. We did that. And so then when we do the car not starting and the motorbike starting, 0.2 times 0.6 is going to be 0.12. And then neither one of them starting would be 0.2 times 0.4, so it would be 0.08. So if you add those up, so 0.48 plus 0.32 plus 0.12 plus 0.08, you will get 1. And that will always be the case when you do your tree diagram correctly. Part D, find the probability of at least one vehicle starts. I suggest you pause the video here and try to do part D on your own. One efficient way to do the probability of at least one, would be to do the complement. So it would be 1 minus the probability that neither start, or none start, but neither since we only have 2 items. So that would be 1 minus the probability of neither of them starting, 0.08, which is 0.92. So the alternative way of answering part D would be just to add up these 3 scenarios where you have either they both start, or the motorbike does not, car does, or the car does not and the motorbike does. You get the same result. Number 2, a packet of seeds contains 40% red seeds and 60% yellow seeds. The probability that a red seed grows is 0.9 and that a yellow seed grows is 0.8. A seed is chosen at random. We're going to use a probability diagram to determine these probabilities. So take a minute and draw the tree diagram. Okay, so you can see I have red and yellow, so I just used the letter R and the letter Y. And then for grows, I just used a G, and then for not grows, I used G prime. I could have also used a capital N for like not grow, but I really need to define these variables that I'm going to use. but we're going to just skip over that for this example. So for part A, the probability of the seed the seed is red and it grows. So we want to write the proper notation, probability, red and grows. And of course you could use R and G. That would be 0.4 times 0.9, so that would be 0.36. Okay, and then for part B, that the chosen seed grows, that's the probability that it's red and grows, or, so and, sorry, an add. So whenever you say or, you can use an addition. So probability of yellow and grows. So that would be, well, red and grows, that's our answer to part A, so that's 0.36. And yellow and grows, that would be 0.6 times 0.8. And so when you calculate that, you're going to get 0.84. All right, now we're going to talk about conditional probability. So let's say, back to our tennis situation, 10 students played 2 tennis matches each. What's the probability that a student won his first match if it is known that he won his second match? So I'm going to circle all the situations where the player won their second match. Student number 1, student number 2, number 3, and then 7, 8, 9, 10. So there are only 1, 2, 3, 4, 5, 6, 7 students who won their second match. So that becomes your denominator. Whatever follows the word if, or we'll see in a second the word given, that's going to be your denominator. So we're saying if we know of the people who won their second match, which is 7 of them, what's the probability that they also won their first match? So now looking at those 7 that we've narrowed down that I circled over here, how many of them also won their first match? So student number 1 did, student number 7 did, and student number 8 did. So that's 3 out of 7. And that's conditional probability. So for our laws of probability, so these are some of the laws. You might have these in your notes. For mutually exclusive and inclusive and independent, these were covered in previous lessons. So for conditional probability, the formula is this. You're going to have P of A, and then you have this vertical bar here, and this would translate to the word given. So the probability of A given B is going to be equal to the intersection, the probability of A intersect B, remember that's going to be the word and when they're intersecting, divided by the probability of B. So that's our formula for conditional probability. Let's do this. Let's do an example where we're going to do conditional probability in a Venn diagram. So we're going to find the probability the student selected at random studies chemistry if it is known, there's your condition, if it is known that the student studies physics. So using our proper notation there, we can say the probability of chemistry given physics. So with that formula, it's going to be the probability of chemistry and physics divided by the probability of physics. That's your condition. Remember, that's your denominator. Whatever your condition is, that becomes your denominator. So looking at this Venn diagram, the probability that they study chemistry and physics is going to be the 15, and we need the total here. So we don't have the total anywhere. So 4 plus 15 plus 2 plus 9, the total there is going to be 30. So this would be 15 out of 30 for chemistry and physics. And then the probability of physics only, well, that's going to be everybody that studies physics. 4 plus 15, so that's 19 divided by 30, which is going to be 15 divided by 19. Now, it seems like kind of a lot of work to do the whole, just do chemistry and physics together, and then let's do physics only over the total. When you can kind of see, well, if it's known that the student studies physics, then your denominator is going to be, we're only concerned about the physics circle in our Venn diagram. So out of that physics circle, how many of them study chemistry as well? And so this is 15. So that's kind of a quicker way to get there with the end of Venn diagram. So it's just going to be 15 out of everybody in that circle, which would be 19. Okay, now we're going to do conditional probability using a two-way table. Now you're going to study two-way tables more in depth in a future lesson. But what we have right here is people exiting a new ride at a theme park were asked how they liked or disliked the ride. So we have this column represents the number of children that were questioned and their responses and the number of adults that were questioned. And then these are they answered that they liked the ride, and then these did not like the ride. So find the probability that a person selected at random is an adult given that they disliked the ride. So if we want to go through the formula, we can say we want the probability that they are an adult. This is probably me. I don't usually like rides at theme parks. Disliked, and that's going to be the probability that they are an adult and they disliked. So intersection, probably adult and disliked, divided by the probability that they disliked. So adult and disliked, that's this number right here that would be 30 out of your total, which is 130. So that numerator would be 30 over 130. And then your denominator for the probability of disliked, well, this is everybody here. The 47 are the number of people that dislike the ride. So that would be 47 divided by 130, which is going to be 30 divided by 47. Now, just like with the Venn diagram, you can do this a little quicker by just saying for your condition, you're only concerned about this row of the people that dislike the ride. Well, really just the 17 or 30. And you're like, of these people that dislike the ride, how many of them were adults? So 30 out of the 47. So you can do it pretty quickly when you have the two-way table. Next up, conditional probability using a tree diagram. So this is that same question we just did a minute ago where we have the red seeds and the yellow seeds. Same probability, and in fact, I just copied over the tree diagram from when we did this example earlier. But now we've got the question, given that the seed grows, calculate the probability that it is red. So let's write down, let's put it all into the formula. The probability of red, given that it grows, so that always follows that little vertical bar there, that's going to be the probability that it's red and grows, so the intersection, red and grows, divided by the probability that it grows. Well, if you look back at the other time that we did this example, it would be example number 2, the numerator is actually the answer to part A, and then the denominator is the answer to part B. So what we have here, we'll just work this out again. Red and grows would be 0.4 times 0.9. And then the probability that it grows, remember that's going to be red and grows or yellow and grows. So, and then you add those together. So 0.4 times 0.9, so it's red and grows, or, that's why we're having addition there, yellow and grows, 0.6 times 0.8. And so when you work that out, and we round to 4 decimal places, that's going to be 0.4286. Next up, we're going to talk about independence and ways to determine if events are independent. So 2 events are independent. I know we briefly talked about independent before. If the knowledge that one event occurred will not change the probability of the second event occurring. So if A and B are independent, then a few things would be true. The probability of A given B would be equal to the probability of A. The probability of B given A would be equal to the probability of B, or the probability of A intersect B would be equal to the probability of A times the probability of B. So that's your multiplication rule right there. So you can use any of these to test for independence. Let's have a look at example number 6. The San Diego Police Department believes there is a link between the release of car-based movies and speeding tickets. Looking at their records, they determined that the probability of A is 0.2, and then here it says A would be car-based movies are in the theaters. The probability of event B, where B is increased in speeding tickets, is 0.15. And the probability of their intersection is 0.03. So we need to determine, is there actually a link between the release of car-based movies and increasing of speeding tickets? So we want to check for independence. So we want to say the probability of A intersect B. So we're basically using this version of the test since we have that. Probability of A intersect B is 0.03. So we want to test to see if that's the same thing as probability of A times the probability of B. So we're looking at 0.03. Is that equal to the probability of A, which is 0.2, times the probability of B, which is 0.15? And you would calculate, and in fact, they are the same. 0.03 equals 0.03. So events A and B are independent. So this then means that the data does not support a link between car-based movies in theaters and speeding ticket increases. All right, our last example. Events A and B have probabilities. P of A is 0.4, P of B is 0.65, and the probability of A union B is 0.85. So first they want us to calculate the probability of A intersect B. So we have to go back to the formula for, I don't remember the kind of events it was, but it was probably that one that has the probability of A union B is equal to probability of A plus the probability of B minus the probability of A intersect B. This is a formula for inclusive events, so events that can happen at the same time. All right, so we have their union, 0.85, and the probability of A is 0.4, plus the probability of B is 0.65 minus the probability of their intersection. So we're going to solve for their intersection. And when you do that, you're going to end up getting 0.2 is their intersection, the probability of A intersect B. So that's our answer to part A. All right, then for part B, they want to state with a reason whether A and B are independent. So let's check for independence. So that would be the probability of A intersect B. Is that equal to the probability of A times the probability of B? So the probability of A intersect B is 0.2. So we want to check and see if that's the same thing as 0.4 times 0.65. And that's 0.2 on the left, and that's 0.26 on the right. These are not the same thing. So no, A and B are not independent. Best to say not independent. Don't say they are dependent. Not independent. The end.